big applause for Professor Stan Matwin.
Thank you. Thank you. Dziękuję bardzo. Can I be heard in the back of the room? The voice all right? Okay. Let me thank first the organizers for having me here. It's always nice to come back to Poland. It's particularly heartwarming to come to a university like this one and see that the Polish universities, of which I am a product in a certain sense, are doing so well. It's a real pleasure to see this. So let me just start by showing where on earth is Halifax. So this is Canada. We are in the very east here. So Boston will be around here, New York City around here, Montreal around here, and we are in the east. And as Dominic said, I wanted to mention that we are the site of KDD, which is Knowledge Discovery and Data Mining, the ACM conference for this area, in exactly 11 months. We are the 2017 edition. The 2016 edition just took place a month ago in San Francisco with 2,700 attendees. So everybody's warmly welcome. I don't know if we will beat the San Francisco number, but as Dominic observed, you can sail, swim, or even kayak from Gdańsk to Halifax, so I hope some of you will come. These are, to encourage you, some of the views. So this is the city of Halifax, and we have some of the very nice places just an hour out of the city, many beautiful sights to see if you come to Halifax, so everybody's warmly invited. For my talk, very briefly, what I will do, and really the take-home message here is that as I have discovered, and I suppose that may also be an interesting discovery for many of you, there is a fascinating new data out there, which is often publicly available, and that data is just begging for intelligent analysis. And not only that, but I personally think, and I will try to convince you, that working with that data and getting results may help us to assist humanity in addressing some of its very serious problems. So in terms of the impact of the work we're doing, I think this is a potential for very significant research that may translate into really important results. Since I'm a machine learning person originally, I will of course take the machine learning view. So technically what I will be talking about are two machine learning experiments that we have done on this data. This of course is early work, and I think in a few years our fantastic papers may be covered by dust a little bit, but I hope that it's just the beginning of the road for the community in terms of working with this kind of data, and ocean data in particular. So this will really be my take-home message. Look at ocean data, a lot of opportunities and a lot of needs out there related to this area. And that's why I think, as Dominic said, I'm particularly happy to be able to talk about this in Gdańsk here. So let me say a few words, and I think this is what most of the people realize, but in fact, 70%, about 70% of the globe is water, oceans. And so, as the American science fiction writer has observed, the planet's called the Earth, but maybe it should be called the ocean. Not a bad idea. And so, oceans are here. They, of course, are the #1 factor influencing climate change. So, very important, but if we look at it from a more mundane point of view, it's a source of protein. Fish and other seafood is the source of 15% of protein for a majority of the humanity, for 4.5 billion people. Oceans provide livelihood for about 10 to 12% of the world's population, so every 8th person on the globe lives off the ocean. And on the other hand, we don't know all that much about oceans. It's surprising that while we know quite a bit about the map of the moon, we don't really have such a good idea about the map of the sea floor. And there is, for instance, little known border dispute between Canada and Russia about the exact borderline on the sea floor between Siberia and North America. And if you think 100 years in the future about exploration of the minerals on the sea floor, this is a very important problem. And we still don't know how this goes because we don't know where the mountain chain is. And it's very hard actually to find out the details at the depth of more than 2 kilometers. So this is really the last frontier. But what's fascinating, and this is what I have discovered since I have moved to Halifax, is that this is just about to change because there is a new technology of sensors and underwater observing devices that will and are, as we speak, giving us a much better idea about the oceans, what's in them, how do they behave, and also what is on the ocean, so to speak. And this is the kind of data that I will be talking about. So we are witnessing, and this is my last bullet here, we are witnessing a very quick infusion, technological infusion of the whole ocean scene, from ocean biology to ocean observation. And if I have time in the end, I will give you a few more details on that. It's fascinating. So the first thing and the data that I wanted to talk about is something that's coming to us from what's called the automatic identification system. I'll be referring to it as AIS. This is actually an idea which is about 10 years old now. It's a standard that has been first produced by the, and sort of introduced by the International Maritime Organization together with the International Telecommunications Union. This was introduced for ship safety, and it's mandated by IMO, so this is a global sea governing body, that every ship beyond 300 tons needs to carry a transmitter, and that transmitter constantly sends a signal that gives basic information about the ship. That information includes the position of the ship in terms of its geographic coordinates, its course, its speed, its identifier, the so-called Marine Mobile System Identifier, MMSI, and possibly some other data. And this is emitted by the ship every 6 to 120 seconds. And it goes out. The idea was, as this little picture shows here, that ships may receive this signal from other ships, and in poor visibility conditions, ships would know that there is another ship coming, and there is a potential for a course collision. That's really how the system was started, but as it often happens with technology, other uses have been discovered. Particularly, rather than just receiving this signal on ground and shore stations, which is essentially for the kind of transmission that's there possible only up to the horizon, because the signal goes on a straight line, it's been understood that the signal going out of the ship can actually be received by a satellite. And this is where the game starts, because that way we have a system of satellites around the globe that constantly receive the signal. The AIS signal is open. It's not encrypted. So anybody with a satellite receiver can actually receive the signal. And you can do it yourself. You can walk into an electronics store here, buy a software radio, grab from the internet instructions of how to tune it, put it on the roof of this building, and you will be receiving AIS signal from the Bay of Gdańsk. Of course, if you have a satellite ground station, you can receive this signal globally. So this is, I claim, big data, because 400,000 ships are sending the signal constantly, all the time. There is about 100 million records that come to the ground station and satellite station per day. And so, you know, significant data. Let me try to see if I can show you a little picture here of what some of the problems are. So this video here is from a Canadian company that's an aggregator of this type of signal. And think for a moment that you are a ship here somewhere in the Indian Ocean that's sending the signal. So you see that at some point, a satellite here shows up that will receive your signal. You will be under the satellite coverage, but only for a certain time. And then there will be probably a gap for a while until the next or the same satellite comes and sees you again. So while we have this data about ship movement, there are gaps. And that's one problem that we have with it today. Now, this problem will disappear literally in 2 years because the number of satellites in service that are receiving the signal will actually grow an order of magnitude from about 11 today to 57 in the end of 2017. Fascinating how this data is being invested in and collected by much larger numbers. So in about 2 years, we will have complete real-time coverage of this data. And indeed, the volume of the data, as I will mention that in the end, will grow. And I say that this is an example of big data, and this is my illustration that I show. So and some of you may have seen in some of the talks I was giving in Poland this spring. So here's the amazing thing, this picture here. What it is, that's why it's amazing. It's simply a heat map of the AIS signal over a 30-day period. So the signal is collected, and it's simply mapped on the globe. Its geographic coordinates are mapped on the globe. And the brightness of the color is proportional to the frequency of ships in that particular small grid of the map. And that's all there is to it. So what it means is that this picture shows where ships go and where they don't. Right? So these are, of course, dark areas, because these are continents. And the amazing thing is that if you look at it, we get the map of the world. Even though there is no underlying concept of geography, continents, and so on. This is just the representation of ships on the globe over 30 days. Right? And this is what big data will do. That's my message, that it will collect the data in which a single instance of the data, a single data point, is perhaps not that significant. But when we put it together in the right way, we get something quite deep. After all, it took humanity millennia to come to the point of being able to build this representation of its globe. And this can be done in a matter of minutes using AIS signals. So this is quite interesting and powerful, and of course has many interesting applications. Some of them I will exactly illustrate here and tell you what we're doing about them. Just some of the issues with the data. I have already mentioned data gaps, because you will not be covered by a satellite. Of course, there is a lot of noise in the data, because either these emitters are not correctly initialized. There's a human operation at the beginning of each trip that needs to set them up, and people simply make errors, or people on purpose manipulate the signal so that, for instance, a fishing ship shows up as a ferry or a passenger ship, or in some extreme cases, they turn off the emitter completely. And this is, of course, a problem because the ship is not visible. This actually is illegal in the territorial waters of many countries now. And if there is a ship that's present in the American territorial waters, for instance, and the signal is turned off, he is in contravention of the national regulations, and he will be apprehended by Coast Guard and respectively punished. So I think that problem will disappear with time, and there are also technical solutions I will mention in a moment. So I claim that this is big data, the AIS signal, because it has these 5V characteristics that we usually like to associate with big data. There is the volume. So let's say, as of today, in my lab, we have about 1.3 terabyte of AIS signal from 2012 to 2015. And for 2016 alone, we will have 3 terabytes received, and we will have probably about 15 terabytes next year. That's our prediction. So, so this is kind of consistent with a little known, or too little known perhaps, memory by Usama Fayyad, who's one of the pioneers of data mining. And Usama has made this empirical observation called memory law, which is analogous to Moore's law, and it's quite fascinating. And it actually works if you follow it. The observation is the following. We know that Moore's law says that the capacity of processors doubles every 18 months. If you look at capacities of memories, the same observation shows you that memory capacities double every 9 months. So if you think about it, it means that our ability to process the data we produce decreases exponentially. And that's a very serious problem. So we better do something about it. And I claim that machine learning is at least part of the answer. So this is just an observation that justifies our forecast of how the data is going to grow. And I claim that this is going to be the case. So we certainly have the volume, and we can have a discussion later what this volume could and could not be if you want to have a big data label on it, but it's there. The velocity part of big data, of course, means that this is its data stream. So the data is continuously produced, and indeed, you know, as we speak, and as I stand here, there probably has been 20,000 records sent to Earth by these ships. So it, you know, it grows 24/7, 365 days a year. Variety. To really do the job with applications using AIS data, you have to connect AIS data with another type of data. And this connection is often non-trivial because, for instance, you will have one data set given to you in a tessellation of 1 mile, 1 nautical mile, and another data set will be given to you in a tessellation which is much less regular and much broader. And they have to map the two types of data so they correspond. And they will not have the same frequency and the same nature. Let me give you an example. I have said that these ships may turn off their emitter, and there they become invisible to the system, which is true. But if you manage, even for a moment, to identify a ship in AIS data with the same ship in radar data, then you have him forever. Because radar data, of course, is there regardless of what the ship can or cannot do. And we're not talking here Navy and stealth aircraft and all this. We're talking regular ships. And if you've ever seen a radar picture of the ocean, you will know that ships as large metal objects come out very bright and very visible to the radar signal. So if you can capture a ship in AIS and radar at the same point, and you can follow him by radar, you will have exactly the same information you would have with AIS as you had with AIS, even though he's trying to escape your AIS by turning it off. So here's an example of data integration that gives this data the V for variety. There is, of course, the veracity, which means that there is noise with the data. I talked about that. There's a problem. And of course, the last V is the value. You know, for it to be big data, the data must solve some problems. Otherwise, you wouldn't go through the trouble of collecting and analyzing it. And the rest of my talk will be about that V for value. So what we are doing in my group, we are collaborating with a very good, I think, world-class group in fish ecology in my university. And these are people that look at fish globally, and they ask certain very important questions. Their final objective is here, is to map the fishing exploitation in all areas of the world. And that means that they would like, for instance, to be able to say, with some precision, how much fish is being taken out of the oceans globally per month, and how much it may be in 6 months or 6 years. These are, of course, questions of absolutely capital importance for humanity as such, and I have given you numbers to justify that. Another problem that they're looking, which is fascinating, is this issue of marine protected areas. So marine protected areas are a concept proposed and implemented by the United Nations. And for 20 years now, there are approximately 6,000 areas on oceans that are defined exactly as shapes on the Earth, on the ocean, with several constraints, levels of constraints in respect to human activity in these areas. Some are purely non-entry. Ships are not allowed to enter there. Some will be no fishing, so ships can enter but do not fish. And some will even allow fishing of a certain kind. This has existed for 20 years, and people are now asking, does this work? Which means, can we prove that there is more marine life in what we call the water column? So imagine, you know, sort of a slice of the ocean from the marine protected area on the surface down to the ocean bottom. That mass of water, is there more marine life in that water than outside because it's protected, or maybe not? And how do you answer this question? So there is no good way of scientifically answering this question. And what biologists propose is very interesting. It's not a proof, but it's a very strong conjecture, and it goes like that. If there is more fishing activity going on the outskirts, just outside these areas, then it's probably because there is more fish in those areas than elsewhere. Because the fish, of course, don't know where the border of the area is. They will go out, and the fishermen, and I'm talking about here these huge fish factory ships that will come and take fish in massive amounts, they will be there waiting for them because it's a fertile ground, if there is more fish. So what we need to do as scientists is to answer this question. Is there more fishing activity outside in the immediate vicinity of the ocean protected areas or not? And if there is, what it is quantitatively? This is the question that my marine biologist colleagues came to us with. And of course, to answer this, we need to use the data, and of course, it's AIS data that we will use. And looking at this data, we need to tell the type of the vessel, we need to tell the type of what they call gear, which is essentially the type of the net that's being used. And we need to answer the third question, which is this fishing ship fishing or not at the given point? So these are the three questions that we need to try to answer. You can answer all these three questions looking at the tracks of the ship. It's very interesting, I've learned that, because if you think about it, the type of the net dictates the mechanics of movement of the ship in the ocean to catch things in the net. And I will show you examples of that in a moment. So if you know the geometry of the trajectory of the ship, you can tell the type of the fishing ship, you can tell the kind of fish that's being taken out, and it turns out you can tell whether in a given point of the trajectory or segment of the trajectory there is fishing or not. These are the problems they brought to us, and as they say, to a man with a hammer everything is a nail. So since they came to us, and we are a machine learning group, we said, oh wow, these are just classification problems. And of course they are, but it's not as simple as going to R or Weka or what have you, grabbing a classifier and running it on the data. I can assure you it's not that simple. We have now spent about 18 to 24 months working on this, and I think we now know how to do it. And this means that we have understood the challenges, and particularly the issue of data representation, which anybody in applications of machine learning will tell you is the key. You may have an application, it doesn't really matter at a certain level what particular type of classifier, whether it's a neural network or a support vector machine or a decision forest you use. Most of the time, that will have much less impact on the quality of your results than the representation of the data you use. And this is where we spend most of the time. That's what I will be talking about. So we've done this classification of trajectories from AIS data by ship type. And we have also done, that's the main work, that's a much harder problem, to look at the trajectory of a ship, of a particular type especially, and tell whether in this part of the trajectory he's fishing or not. So, like I said, the representation is the key. And so, of course, you know, we looked at the existing work. There is a lot of work in a trajectory representation. This has been a topic of particularly intense research since cellular telephone data has become available. There are semantic trajectories by Spacca-Pietra. There's been a whole concerted effort here in Europe, mainly in Italy, looking at human trajectory data from mobile phones and GPS devices on cars. There is some work done by a group at the NATO Research Center in Italy with ship data. There is some work done in our group as well lately, especially on trajectory segmentation, and I will talk about that in particular. But what I want to say is that the work on human trajectories doesn't really apply to ship trajectories very well, because humans, for instance, move and stop very often in their daily activities. You know, we are all sitting here, and I'm sure the local cell phone operators here in Poland can tell that there is a meeting going on. There's a whole bunch of people stationary in that cell of the grid. Ships are not like that. Ships are moving all the time. And this is one of the reasons why trajectory representation methods worked out for human mobility do not translate very well to ship mobility. So here's a picture that says a few things in a very condensed way. There are turns out, three major types of fishing ships. And you know, this is fascinating. I've learned that, again, in the last 3 years. I had no idea about that. Before going to live in Halifax, I knew about as much about the oceans and fishing as somebody that likes going to seafood restaurants, and so not much. Turns out there's a very old and intense area of human activity. And so we have three basic types of fishing ships. I will only talk about two here. One are the trawlers, and the others are called longliners. They're very different in terms of their operation because the nets are different. Trawlers are essentially huge bags, so to speak, that a ship drags behind him. And he essentially moves in elliptic types of shapes and drags that in the ocean and catches ship in that sort of bag and then pulls the bag out and it's full of fish. Longliners, totally different. Instead of a net, there is a very long line, and on that line there are hooks, and fish come and, you know, unfortunately swallow the hooks, and they are hooked, literally. When I say very long lines, they are up to 100 kilometers in length. So a ship will drag that, and then these ships, instead of like trawlers moving in elliptic shapes, they actually move in zigzags, because they have to pull that line in every so often, and when they do that, they have to go on a straight line. So they will go on a straight line, pull the line in, drop it back, zigzag, and this is their move. So you see already that the geometry of the ship dictates the type of the ship. So the gear or ship classification isn't all that hard. What is much harder is to tell whether a ship is fishing or not. So here's an interesting observation. For trawlers, these are the distributions of speed values, and unfortunately, the color isn't very good here, but this is blue, and this shows non-fishing, and this is, I think, black and shows fishing. So the idea is that when the ships fish, they move faster, interestingly enough, than when they do not fish. So looking at the speed alone that you get from the AIS signal, you can tell, by and large, quite well, whether a trawler is fishing or not. So that's good news. However, for the longliner, the two speeds basically coincide. Right? The distributions are very, very close. So you can't tell whether a longliner is fishing or not by the speed alone. And this is where the difficulty is. Right? So for trawlers, there's perhaps a solution that's not that hard. For longliners, this solution completely fails. We have to do better than that. Let me tell you a little bit about the data we worked with. So this is particular sample, quite small sample in a way, but the largest published, I think, of data from AIS used for this problem. We had 83 vessels operating mainly in the North Pacific region. We had about 200,000 for trawlers, 200,000 points, so trajectory points literally on the ocean, collected in July 2013. That's what we used for training. For testing, we used vessels between January and October 2011 to 2015 with about 800,000 points. For longliners, we have only had 16 vessels, so many less, for that 2-year period with about 570,000 points. And two comments I wanted to make here. The first is that, in my opinion, this is something I have learned working on this project, it's really important to look at this data through a different lens that a classical machine learning researcher will. Because a classical machine learning researcher, and I've seen that done, and I think it's totally incorrect, will take this data and use it in a standard, we'll put it all together, and we'll use it in the standard cross-validation experiment, which I will not, certainly do not have to explain here. This is totally wrong, because you mix in training and testing the same ship. The important thing is to construct your training and testing set so that you use one set of ships for training and another for testing. Because otherwise, I claim you will have a data leak. And of course, data leak puts in question all your results. So one has to be very careful to design a training testing regime to avoid a data leak. And this is one technique. It's actually an instance of something that's well known. And you know, I have advocated that in the field for many years with some success, which is called LOBO, which stands for leave one batch out. The data very often comes to you in natural batches, and since your machine learning system will be trained on one set of batches and used on another, this is the only reliable way to train and test, and forget the cross-validation. Anyways, that's one message. The second message is that the practical difficulty that you had here, and we were lucky, very lucky to have a solution in-house, is that, of course, to build a training set, we needed somebody to sit down, and for that problem, phishing, non-phishing, to look at the trajectories and label each point as to whether the ship is phishing or not. So it has to be a person with some knowledge of phishing, and also, frankly, somebody very patient. And we had in the biology team a PhD student, see, most of the good science is done by PhD students, who spent months, literally, sitting at the computer screen and clicking on these points and saying phishing, not phishing, with her understanding of fish ecology, how fishing ships operate, and so on. So she's, you know, certainly one of the authors of this work, because without her doing that effort in a reliable way, we wouldn't know. There's another, of course, very interesting problem that I raise when we have discussions with our biologist partners. So we bring them the results, and we say something like, well, we have 85% accuracy here. And they say, no, no, this isn't good enough. We want 99% accuracy. And I say, no, this really doesn't make much sense, because if we had two experts, the only way to say what is a reasonable number is to have two experts, have these experts label the data, and then go and measure a measure like Cohen-Kappa that essentially gives you the degree of agreement between two sets of labelings, human labelings. And then you would know if humans actually disagree and at what level. I can guarantee you that humans would disagree between themselves. So we should only be asked to produce something that is not inferior to the level of human-to-human disagreement. I think it's not right to ask a machine learning system to perform better than a human, or at least in general, it's hard to do. All right, so we have some published results. I wanted to mention that this published work that just has come out in May is something that we have done already. My presentation is not about that. Anybody who's interested in this is welcome to go to the paper. It uses different methods. In particular, for trajectory segmentation, is using a mathematical biology technique algorithm called the Lavielle segmentation, which is based on a very interesting idea from so-called habitat analysis, which is an analytical technique to analyze animal movements, used first on mammals in Africa and then adopted to oceans. And then this sort of a leap observation has been done around 2007, I think, after this paper has come out, that says that, that fishing ships actually move like big ocean predators, whales, sharks, and so on. That since they chase fish, the movements of fishing ships will be similar in terms of the geometry to movements of large ocean predators that feed on fish. So based on that, there is a technique to segment the data and so on. Segmentation, we have understood, is very important. So instead of working at the level of individual points, you will try to put these points together, interpolate so that you have lines, and then you have to divide these lines into meaningful segments, meaningful in terms of fishing or not fishing. So this is the challenge we had. And you know, finally, we have gone to something very old and very wise, which is the essential fundamentals of human ocean navigation. And it turns out that in there, every sailor here will know, there is a concept, a basic concept of bearing. Bearing is the angle degree between the course of the ship and the north. There are, in fact, two bearings. Could be a geographic bearing or a magnetic bearing. whether you refer to north or geographic or magnetic. That's not all that important. The interesting thing is that due to the shape of the Earth, this bearing has some very interesting properties. So here's a little illustration. You see I sort of combined, there's a line going from point A to point B on the Earth. So this is how an airplane would fly from Baghdad to Osaka. So they happen to be at the same longitude, 35 degrees, and the latitudes differ by the quarter of the globe. But if you think about it, when he leaves Baghdad, he will sort of go under that angle when I look at it. So that will be 60 degrees. When he arrives in Osaka, he will arrive like that. So that will be 120 degrees. From the point of view of just a projection geometry, of course, this is just a straight line. But we can't look at it like that. If we want to represent trajectories, we need to work with bearings. This is what we have understood. And then, of course, there is a way, and we know that, I suspect, from 15th century. Here's how you can compute your bearing. If you go from A to B, these 2 points are given to you in terms of their geographic coordinates. You plug in these coordinates into this formula, and then you can work it out. It's high school geometry. And then this gives you the bearing on the start, if there is no obstacles and you really move on the ocean on the straight line. So this is very interesting, and this is something that I suspect Christopher Columbus knew, and that's what allowed him to sail from wherever he started. There's still a huge dispute around that, to wherever he finished, which is not yet decided, roughly from Europe to America. All right, so this is fascinating, and we have used this bearing idea to essentially segment trajectories. And very briefly, I won't go into the details. We look at a pair of points, and we see if there's been a critical change of bearing, where we have given this word critical some technical data-oriented meaning. Is there a sharp way, sort of a turn, or it's not sharp enough? And if the turn is sharp enough, then we say, okay, this point where the turn occurs is actually a point where the trajectory ends. Sorry, not a trajectory, a segment of the trajectory ends. So we segment trajectories in that manner based on the bearing, okay? And, you know, I'm not going to go into the details. This works very well, because if we compare to Lavielle, and so we use Lavielle for the segmentation, so we have to assign each point to a given trajectory, a given segment or the next segment. You know, we have only about 50% of points which are strictly speaking about being part of this segment or that segment, and we have 44 points that are kind of in doubt, and we have to assign them somehow, where this number is much better for the bearing segmentation that we have done. So you have much more certainty in doing this segmentation than doing that. So this is why we think this method works. And also, just visually, this is a set of ship movements on the globe, somewhere, I think this is North Africa. So a fishing ship moves here, and the red points denote the segments, beginnings and ends of segments. But when this is the Lavielle method, and this is our method. So you see that our method is much more fine-grained in terms of selecting these trajectories, just visually. And then we have done some machine learning here. So very briefly, what we use here is information about points as we get it from AIS. So remember, there is there's the position, but the course and the speed, particularly. The position, we relativize it. We don't use specific values of where the ship is. We just use relative, so we're not bound in the results of machine learning to a particular geographic coordinate on the globe, of course. And so, so we use this point information, and the most important thing is that we also use, for a given point, this context information about the segment to which the point belongs. So for that segment, which we have just obtained in the way that I have described, we actually compute the average speed throughout the segment, the average course, and I think another quantity that I don't quite remember. So this is for the whole segment. That's why I call it the context. So we have these two things. Then we use this particular classifier. I'll mention it because that gave us slightly better results than others, but it's not all that important. In fact, I'll show you another approach in a moment. We use decision forests and specifically ensembles of Breiman's decision forests that gave us the best results here. And we have done, of course, experiments on trawlers, but since trawler data is limited, we have actually trained on longliners and used it on trawlers, interestingly enough. And what made a big difference in results is whether we include in the data points that are closer than 10 nautical miles to shore or not. And the reason for this being important is that close to shore, ships move governed by other reasons than just fishing. They have to avoid other ships. There's often regulations that will be specific to a port into which they come and so on. So this area of close to shore should really be treated differently. This is what the results tell us. And since there isn't a machine learning talk that doesn't have a table like that, mine is here. But of course, the only important thing is here at the bottom. Never mind these. These are 6 particular vessels on which we tested the prediction on longliner trained trawler movements. And so the results we get are just about 87% accuracy. Since there is a slight imbalance in the data, when we represent the results, we should really also show something like specificity and sensitivity. So we do give it here. Never mind, 87%. If we know about the distance to shore and we can eliminate the closer than 10-mile points, we go up to 91%. And interestingly enough, so this is what I said, it's kind of a transfer learning because we train on one type of ship and apply to the other. If we do it within one type of ship, train longliner, test longliner, it's actually just slightly better. But we're getting to some quite respectable results here, above 90%. And this I will skip because I'm running out of time. I will just very briefly mention that we also looked at applying this method to another type of mobility data. And in mobility studies, there is this canonical data set published by Microsoft, which is human mobility data from cell phones in Beijing from 2007. And this method has about, the published result, the one to beat, is about 71%. So I'll show you some results on that. Now, I have limited time, so I will very briefly run through this, but we have now used deep learning on this data. So I can tell you that it took us about a year to really bite into the deep learning papers and understand more or less what to use. It's a very tough domain in terms of trying to use the tools that are out there and the methods correctly. It takes time to understand what from the toolbox, what is the right method and approach. So what we have done, well, we worked with the same data as in the previous approach. We use recurrent neural networks. The reason we use recurrent neural networks is that this is a technique designed for dealing with sequence data, which is essentially the trajectory data, right? And I will show you some pictures, but the idea is that you build layers of the network such that each layer essentially corresponds to a point in your sequence. And these layers have sort of a ability, and you use the same training approaches at each layer, and you share the weights between layers, and that gives the system the ability to know about its performance on the past points, but also on the future points, as I will show. Future, of course, if you have batch data, this is what we have. And then this has some well-known problems in the neural network domain. So we have applied the tools that are recently proposed. We have successfully applied the tools that are recently proposed for this problem, the so-called long-term short long short-term memory, terrible name, by the way, long short-term memory. And then, you know, what took us probably 9 months of the 12 is to use a bag of tricks that you need to use in deep learning to get any results at all. I will mention these. So the first thing is that we did was to discretize the data, which turned out to be very important. And the reason is very simple, conceptually. I'll show it here. If you work with neural networks, what you do, of course, you build linear models at each level, right? So if you think about it, if you have data that's more or less normally distributed, you're out of luck right at the beginning, right? Because you're trying to build this kind of shape, a line, to model a normal distribution. So you're likely to do much better if you do something extremely simple at the beginning. Instead of working with all the data like that, you discretize it into, say, 3 intervals. So here, here, and here. And then a linear shape will be a much better approximation of data in each part than it was for the whole thing. So discretization seems to make sense conceptually, and I have results to back up that statement later. Okay, so discretization. Here is this recurrent neural network. So essentially, you take a neural network in which you have this layer per weight, you unfold it, and it runs like that, and it has these states, so it moves from state to state. If you were to totally ignore that layer with weights, the unfolding of the weights, you would have a standard feed-forward network. Now, because you have the weights, and the weights, you know, transmit that information between states, these further states are informed about the action of the network at an earlier stage. This, like I said, has well-known problems, because essentially what happens is that you, since you work with these gradient methods, typically, these gradients may get very small or very large. Now, since of course you multiply them in your feedback part of the network, then if you multiply very small numbers, you get something extremely small. So this is the vanishing gradient vector. Symmetrically, you can run into the exploding gradient problem, and this is what these RNNs have. So people have come up with this idea. In fact, it's a 1979 paper from Schmidhuber's group called long short-term memory, which is the craze of the field now. Everybody's using this, only 37 years after it's been published. So you have to be a little patient to get the impact of your work. And so the idea here is that you equip this recurrent neural network with a kind of memory about past states and the values in these states. And that memory has the ability to forget if the forgetting is dictated by a kind of sigmoid function. Very quickly, I don't have time to spend on this. So this is what happens, and that's what you use to kind of address this vanishing or exploding gradient problem. And then you build something called bidirectional long short-term memory. Sorry, long short-term memory. So this is how it looks. The big idea here is that the output at each level depends on the backward chaining and forward chaining of the data at this hidden unit. So this is one kind of a layer of bidirectional short-term memory, and then you can build these layers up. So if you build them up, you have this kind of structure of your deep network. And it turned out that for the ocean data, it was sufficient and adequate to have a 2-level bidirectional long short-term memory network. Wow, okay. So 2-level bidirectional long short-term memory network is good for ocean data, but it's not good for human mobility data. And I will show you that very briefly. And like I have said, very significant engineering effort, and I use that engineering word here in a very positive sense, went into massaging these methods with all kinds of additive algorithmic tricks to get the results. This involved, so first of all, we use the Google TensorFlow system. This is the one that, in our opinion, and this is really my colleagues' opinion because they've done the hard lifting here, is probably the best tool now. We would use it rather than Theano or Café on this type of data. We use this new technique known as ADAM, which is essentially a very bright idea of how to speed up stochastic gradient descent, which is of course used inside all these networks. very, very nice new trick published last year. We use these two other techniques from Benjio's group, three actually, that also have produced better results. And this is what we were getting, more or less. So this is this low ball, leave one batch out. And these are our final results here. So you see we go up to 88.1, which is quite comparable to what we had before with respect to excuse me, the use of Breimann bagged or ensemble trees. So very similar. And on some ships and some trajectories, the longer ones, you see that the results were really very good and close to 100. So we applied the same on mobility data, and here we have observed a very essential importance of how many layers of this bidirectional network we have. If we go to 10 layers, you see how significantly the error drops, right? So this is important, and for human mobility, that's what you need. And with that, we were able to get results, quite significantly better results than the published results for this human mobility thing. Right, so this is what part of the work we have done. We have a paper on Wednesday, tomorrow morning that I'm presenting on yet another completely different approach that we borrow from natural language processing algorithms called conditional random fields. So that's for tomorrow, come to the talk. We of course have exciting plans to do more work. We expect there to be much more data. So in fact, there's a whole layer of this work that I haven't even mentioned at all, which is a very tough set of very tough technical problems of putting this data in some kind of an organized structure so that you can query it, right? And so we use Postgres now, but if we were to use Postgres for queries, we would have to have minutes of time to wait for a query answer. So what we do is we produce something called Sparkle Index, Solar Index from this Postgres to answer things quickly. And with that type of thing, we can produce the kind of heat maps that I was showing you at the beginning very quickly. We also think about moving to other sort of unstructured big data systems of the kind like Hive or MongoDB. There is very interesting work done about standardization. This is something you really need for ocean data, so that people who have ocean data sets will be able to produce metadata that other people would understand. That's really important. There's very exciting work going on that, mainly here in Europe at Ifremer in Brest, in France, and the Irish Ocean Research Center in Galway. You need to think about sort of an ungracious but essential task of building a web interface to all these things so that your ocean scientists can use it. There's, of course, a very important aspect of visualization, and you need to work on that. So we have a whole big plan to do much more work on this. And more importantly, we also have the money, because we have just received a very significant support package from the Canadian Research Support Agency for a project called Marine Environmental Research Infrastructure for Data Integration and Application. And so we call it Meridian. And we will be extending our team quite significantly. So if there are people here that would be interested in working with us for any time between 6 and 12 months, get in touch. Lots of data, lots of interesting problems. I think there's a lot of opportunities to publish this, because this is really uncharted territory with obvious impact on important problems. I will skip this. I will just mention that this is, of course, joint work with a number of colleagues here whose names I just want to put on record here. Particularly Christina Böder is this labeler that has spent hours labeling the data. Lots of ideas on the neural network part come from Xiang Jiang. Of course, we have, as any such project, we have a large number of sponsors to whom we are very grateful. In particular, I have to mention that this work has come to the attention of Google, and we are now supported financially by Google Labs for part of that work for the reasons that I can tell you if there's questions around it. Thank you very much.